Hi everyone and welcome back. We have talked a lot about theoretical concepts involved in deep learning. Today we are going to build a very deep convolutional networks using residual networks. So in theory, very deep networks can represent very complex functions, but in practice they are hard to train. Residual networks allow you to train much deeper networks that were previously practically feasible. And so we are going to perform this task using Keras. So first of all, before jumping into this, let's run the cell and load the required packages. So you need to be very cautious about which packages you are going to import. If you are going to import unnecessary packages, then you're going to increase the load up time for unnecessarily. So make sure you are importing the packages which are really required. So in this case, we are going to import NumPy. Since we are doing this in Keras, we are going to also import all the modules which we are going to use from Keras. So first of all, we are going to import layers, then we are going to import dense layer module activation function, padding layers, batch normalization, and I'll be writing down the code live so that you'll get a fair idea of how you need to go about from scratch. And then we are going to import models which we are going to use. We are going to use a pre-trained model because I have shown you in transfer learning video that it's really recommended that if you are going to use pre-trained model, then you will be spending less amount of time in training your model from scratch. Then we are going to import utility modules, SciPy, and then we are going to import Keras' backend. Note that we are not using Theano as backend here, we are using Tensorflow as backend. So let's start with the problem of very deep neural networks. So previously I have shown you about your convolutional neural network. In recent years, neural networks have become deeper with state-of-the-art networks from just a few layers, like for example AlexNet, to over 100 layers. The main benefit of a very deep network is that it can represent very complex functions. It can also learn features at many different levels of abstraction, from edges to very complex features. However, using a deeper network doesn't always help. A huge barrier to training them is vanishing gradients. A very deep network often have a gradient signal that goes to zero quickly, thus making gradient descent unbearably slow. More specifically, during gradient descent, as you backpropagate from the final layer back to the first layer, you are multiplying by the weight matrix on each step, and thus the gradient can decrease exponentially quickly to zero, or in rare cases grow exponentially quicker and explode to take very large values. So in the graph above, you can see that during training you might therefore see the magnitude of the gradient for the earlier layers decreases to zero very rapidly as training proceeds. So let's start by building a residual network. So in ResNets, a shortcut or skip connection allows the gradient to be directly propagated to early layers. The image on the left shows the main path through the network. The image on the right adds a shortcut to the main path. By stacking these ResNets block on top of each other, you can form a very deep network. We've seen that showing ResNet blocks with the shortcut also makes it very easy for one of the blocks to learn an identity function. This means that you can stack an additional ResNet blocks with the risk of harming training set performance. There is also some evidence that the ease of learning an identity function even more than skip connections helping with vanishing gradients accounts for ResNet's remarkable performance. Two main types of ResNets are used depending mainly on whether the input-output dimensions are same or different. We are going to implement both of them. So in this video I'll be showing you about the identity block. So the identity block is a standard block used in ResNets and corresponds to the case where the input activation, let's say A of L, has the same dimension as the output function, say A of L plus 2. To flesh out the different steps of what happens in ResNet's identity block, here is an alternative diagram showing the individual steps. The upper path is the shortcut path. The lower path is the main path. In this diagram, we have also made explicitly the convolutional 2D layer and rectified linear unit steps in each layer. To speed up training, we have also added a batch normalization step. Don't worry about this being complicated to implement. You'll see that back normalization is just one line of code in Keras. In this video, you are going to actually implement a slightly more powerful version of an identity block in which the skip connection skips over 3 hidden layers rather than 2 layers. It looks like this. So here's the individual steps. First of all, first component of main part. The first convolution 2D has f1 filters of shape 1 by 1 and a slide of 1 by 1. Its padding is valid and its name should be this. So we are going to use 0 as a seed for random initialization. Then the batch normalization is normalizing the channel axis, and then we are going to apply rectified linear unit activation function. This has no hyperparameters. Then second component of convolution path. After that, the second convolution layer f2 will be of shape f comma f and is slide of 1 by 1. Its padding is same, and the second batch normalization layer is normalizing the channel axis, and then we are going to apply rectified linear unit function. This has no hyperparameters. And the third component of main path, so it has f3 filters of shape 1 by 1 and a slide of 1 by 1. Its padding is valid, and the third batch normalization is normalizing the channel axis. Note that there is no value activation function in this component. And then we are going to proceed to the final step. The shortcut and the input are added together. Then we apply the value activation function. This has no hyperparameters. And then proceed to the function. We are calling it identity block, in which we are going to pass x, which is a tensor of shape m comma number of hidden layers in previous layer, number of hidden layers in previous weight of the weight matrices, and number of channels in the previous layer. Then we are going to pass in the filter f. It's an integer specifying the shape of the middle convolutions window for the main path. And then stage, which is used to name the layers depending on their position in the network. And then we are going to pass in block. It's a string used to name the layers depending on their position in the network. So first of all, we are going to define the name bases. So let me just write it down. We are going to convert stage into string for writing purpose. After that, we are going to create a name basis for batch normalization. And after that, we are going to retrieve filters f1, f2 and f3. After that, we are going to save the input value. You'll need to later add this to the main path. Then we are going to first write the first component of main path. Note that you will have to be really careful about the dimensions, because if you're going to specify the wrong dimensions for kernel and the image, your network is going to collapse. So you'll need to be really careful of the dimensions which you're going to pass. So first of all, we are going to construct a convolution 2D layer, and then we are going to specify the filters, which is equal to f1. Then we are going to specify the kernel size, which is 1 by 1 in this case. Note that these dimensions are tested and I've tried it out on my local machine, so there's no need to double check it. And then we are going to specify the slides, and then we are going to set the padding to be valid in this case. And then we are going to specify the name of the layer which we are passing. So we are using Keras functional API. If you are really interested in documentation, you can refer to this website. Keras has really well written documentation, and if you really need to gain more hands-on experience with functional API, you can refer to this documentation anytime. And then we are going to specify the kernel initializer, which is glorot uniform, and then we are going to use seed is equal to 0 so that your output matches mine. And then we feed in the parameter. Then we are again going to use the same component variable, and then we are going to use batch normalization. So we are going to specify the access to be equal to 3, and then we are going to write the name which we are going to use afterwards. So after that we are going to specify the activation function which we are going to use, which is value. After that we are going to write the second component of main path. So it's basically same what we are going to do in what we have done in the first component. We are just gradually building upon it. So we are going to create a convolution 2D layer. We are going to input the filters, then we are going to input the kernel size, then we'll specify the strides, and we'll set padding to be equal to same, and then the name of the layer which we are going to call it afterwards. And then we specify the kernel initializer. After that we are going to use patch normalization, and we'll set access equal to 3. We'll specify the name, and afterwards we are going to use activation function, which is value in this case. And now we'll come to third component of main path. So we are going to use a convolution 2D layer. We'll pass in the filters, we'll specify the kernel size, then we'll set strides equal to 1 by 1. I've explained all the building blocks which are normally used in convolutional neural networks, like strides, padding, in the earlier videos of the playlist. So if you have any doubts regarding what is happening, you can check that anytime. Then we are going to specify the name, again kernel initializer, and then we'll set batch normalization, which x is equal to 3. We'll specify the name, and we are not going to use activation function here. Now the final step, will add shortcut value to the main path and pass it through value activation. So we'll use add module, and then we're going to use activation function to squash these up together for non-linearity, and then we're going to return this tensor called x, which we have discussed about earlier. And then we are going to run the TensorFlow session. So if we are using with tf.session as test or normally sys, then we don't have to use the module.close because TensorFlow already takes care of this. Then we are going to use random seed, and then we are going to make use of TensorFlow Placeholder. So placeholder is a value which, so normally we'll first make the computation graph in TensorFlow, and then we'll run the graph. So placeholder provides a guarantee that it's going to provide the values later when the computation graph will be running. And then we are going to run it. Then we'll run the session, we'll pass in the tensor, and we are going to use feedict. So feedict provides the value to the tensor when we run the graph. And then we'll print out the output. So that's it for part 1 of residual networks in Keras. We'll talk of convolutional block in the next part of residual networks. Thank you for watching this video, and make sure you get the expected output which I have get. And I have used some helper functions, and I'll be linking down to those modules in the description section. So make sure you are actually saving those Python modules in your local machine before running it. And that's it for this tutorial I'll be showing you about convolution block in the second part, and then we'll talk about your ResNet modules, which will contain 50 layers, and it will be interesting to see what interesting things you can come up with your network. Make sure you hit the subscribe button and stay tuned for the next upcoming tutorial on residual networks, and we're going to build up our convolutional block. In this we have built our identity block. In the next one we are going to use convolutional block in Keras. Thank you for watching. Talk to you next one.